Hi, in this video we are going to talk about a more popular way of solving Dijkstra's shortest path algorithm with the help of approximately adjacency matrices. So let's get started. For example, we have a graph like this, A, B, C, D, E, F nodes, and we have of course several edges. It is an undirected graph, so we can get from A to D, for example, and from D to A without any problem. There is no directed edges. And of course, there are several edge weights such as 2, 5, 10, 4, and so on. So of course, we have the adjacency matrix. It's going to represent that, for example, we have the nodes for every column and we have the nodes for every row. And for example, is it possible to go from A to D? We can search it with the help of the row and column indices. Of course, there is no recurrences in the sense that no nodes are connected to itself, so that's why the diagonal values will be zeros. But if the values are not zeros, it means that there is a connection between the two nodes. For example, there is a connection between C and D, and you can read it from the adjacency matrix that the edge weight is 10. Because it is an undirected graph, it means that the edge weight from A to D is equal to the edge weight from D to A. That's why the matrix is going to be symmetric. So the transpose of the matrix is equal to the matrix itself. So for example, we would like to find the shortest path, and the start vertex is the A. And we would like to figure out that what's the shortest path for every other vertex. So we have the starting vertex, the A, and we have the other vertices, the B, C, D, E, and F. We start with A because this is the starting vertex. Because there is no connection from A to A, that's why we initialize it to be 0. It is infinitely close to itself, of course. And at the beginning, with the initialization phase, we set all the others node to be infinitely far away from the starting point. So this is basically the starting point. Okay, we have to track the minimum distance, and where did we come here? So basically the predecessor. Then, for example, on every iteration, we consider the possible routes we are able to take. So we are at the vertex A. We are able to visit vertex B, vertex C, and vertex D, but we are not able to go to E and F because we don't know the structure of the graph in advance. So we can go to B, C, or D. And because that's the minimum value, it's very important. It is the initialization phase. So in this step, it is not so important. But on every iteration, we have to select the minimum value of the row. Because we have the zeros and we have the infinities. Of course, the 0 is the smallest one. And it means that if we consider that what routes can we take, we can come to the conclusion that we have to calculate the minimum values. So for example, for the initialization, we come to the conclusion that B is infinitely far away. But here we come to the conclusion that the cost is 7. So what's the minimum, infinity or 7? For the node B, of course, it's the 7. What's the minimum of infinity and 5? Because it takes cost 5 to get from A to C. That is going to update the value for C. We can get to D with the cost 2, and of course the 2 is less than infinity, that's why we update the value for D. But we are not able to go to E and F, and that's why we just have to copy the values from the row above. And in every iteration, we have to calculate what's the minimum value within this row. We come to the conclusion that it is the 2, so we hop to the node D. Okay, yeah, we calculate the minimum value in every row and we hop there. And we consider that, okay, what are the possibilities now? What routes can we take? We can go back to A, but we have already finished it. We have already visited A. That's why there is a red value in its column. And we have already visited D. That's why there is another red value in the column. But we can visit C and we can visit F. And we have to calculate that is it a shorter path? So for example, we calculate that what's the minimum between 10 plus 2 and 5, because 5, that's what we know for certain, that so far from A to C, the shortest path is 5. But we come to the conclusion that if we are standing at the node D, it takes 2 to get to D, and it takes cost 10 to get from D to C. So we have to calculate it whether 10 plus 2 is smaller than 5. It is not smaller, then we do not change the column C. It's going to remain 5. We can go to node F with the cost 2, so we have to calculate it whether infinity is smaller or 4. Why 4? Because we are standing at D. The minimum cost to get to D is 2. That's the red value in the previous row. And we know that it takes 2 to get from D to F. We can read it from the image on the left. So 2 plus 2 is 4. Whether infinity or 4 is the smaller, of course 4 is the smaller. We have to copy all the remaining values from the row above, from the vertices we haven't visited so far. And we have to find the minimum. The minimum is 4, which is associated with the vertex F. So we have to consider the vertex F. We are able to visit D, but we have already visited it, and B and E. So whether there will be a shortest path when we visit, for example, B, and we come to the conclusion that we have to calculate what was the minimum, 7 or 8 plus 4. Why 8 plus 4? Because it takes 8 to get from F to B, and we have calculated that what's the minimum value from the previous row. It is 4, which means that the shortest path to the F node is 4. So 8 plus 4 is 12. 12 is not smaller than 7, so B remains the same. But the E is going to be updated because it takes 4 plus 6 to get from A to E, and it is initialized to be infinity, so the minimum yields 10. And we have to copy the value, the remaining values from the row above. And we have to find the minimum. Okay, it's going to be the node C, so we have to consider the node C. We can go to A, but we have visited it. We can go to D, but we have visited it too. The only node we are able to go from the C, which we haven't visited so far, is the E. So we have to consider that what's the minimum, whether 10 or 5 plus 4, which is going to yield 9. So we have found a shorter path. What is the 5? 5 is the minimum value in the row above. What does it represent? It represents that the shorter path from A, so from the source to the given vertex, is 5. So that's what we know for certain. And then we have to make these update values. Okay, so copy the values from the row above that hasn't been visited so far. We get the minimum again, and then we go to the node B. We consider that, okay, we have already visited A, we have already visited F, but we haven't visited E so far. So what's the minimum value? The 9 or the 7 plus 3. Of course, the 9 is the minimal, so there won't be any update values. And we come to the conclusion we have visited every vertex in our graph, so our algorithm terminates. And these red values represent the shortest path, the cost of the shortest path. So from the given A, of course, in this situation, A is the source, which means that we are curious that what's the shortest path, for example, from A to F. And you can read it from the table that it's going to yield 4. It takes 4 to get from A to F. You have to go to the D first, and then from the vertex D, the vertex F, 2 plus 2 is 4. Okay, it's working. What's the shortest path from A to C, for example? It is 5. What's the shortest path from A to E? It's going to have 9. You have to go to C first, and from C to E. It's going to be the minimum, the shortest path. And if you would like to get the shortest path itself, then you have to track the predecessors and you have to make these backtracks. Basically, it is the same as we have discussed for the Dijkstra's implementation with linked list representation. So this is the most popular way of solving the Dijkstra's shortest path algorithm. Thanks for watching.